Okay, good afternoon. Let me begin by thanking Kirsten and other organizers for inviting me to be here. Very exciting to be here, though a little bit dangerous, walking on the snow, as I discovered this morning coming in, rushing. So I'm going to tell you about work that we've been doing over the last few years, looking at deformation of glasses um, in an oscillatory protocol, and I had in mind to say a lot more than what I'm going to about the transient regime. So I hope those who have heard much of it already will forgive the repetition, but I see a lot of new faces here, so I hope on average it's going to be moderately interesting. Okay, so this is a quick outline. I also decided not to sort of talk about the general introduction to the problem. I think in a focus conference like this, it doesn't make much sense, but I'll just sort of say what this talk is going to be about, and then go through various aspects of shear deformation, avalanches and transient regime, the yielding transition, and shear banding. This work, as I said, has been pursued over a few years. Much of what I'll talk about is done by Anshul Parmar while he was a student at JNC, and along with a postdoc, Prem Kumar, and a talented young undergraduate student who spent a couple of summers with me. Okay, so basically the topic of what I'm going to talk about is mechanical response of glasses subjected to deformation. You've already heard enough about this. The nature of plastic deformation events in sheared glasses, the yielding transition, and the associated formation of shear bands, and the characterization of avalanches before yielding and after yielding. And as I said, as a significant difference from what you've already heard this morning, we, by and large, I'll be focusing mostly on looking at glasses that are probed through oscillatory shear deformation in computer simulations. Okay, so here's the outline of what we do. We consider energy minimum configurations, which we call glasses, obtained from quenching liquid configurations from high and low temperatures, and when it's quenched from high temperatures, we call them poorly annealed glasses. When they're quenched from low temperature liquids, we call them well annealed glasses. This is a way of assessing the importance of the initial conditions, and by and large, for what I'm going to talk about, initial conditions are not going to be too significantly important when we study cyclic deformation. So we look at the response to affine shear deformations through modifications of the energy landscape and transitions between minima through something called the Athermal quasi-static protocol. I'll describe it briefly. The deformation applied is cyclic, characterized by a maximum amplitude to which you deform the glass. We also look at uniform shear deformation and make a comparison. We study the evolution of plastic deformations, energy, etc. of the glasses through individual cycles of deformation, as well as the number of cycles is increased. And what one normally sees is that some kind of a steady state is reached after the application of cyclic deformation through a large number of cycles. The characteristics of the steady state are investigated, as well as the approach to the steady state. One caveat here is sort of the steady state when one is deforming a glass uniformly usually means, well, it means that you've gone beyond the yielding point and you're in a flow regime. And in the case of cyclic deformation, one doesn't always do so. It depends on the amplitude of deformation, whether you go beyond the yielding point or not. So steady state for us means that after the application of a number of cycles of strain, one has reached a state where the properties of the glasses are not changing, or at least not changing very much. Okay. All right, so here is a quick summary of athermal quasi-static deformation. We subject the energy minimum structures to shear deformation by small increments I forgot to mention, and then we minimize the resulting deformed structures subject to suitable boundary conditions, and the procedure produces a sequence of configurations that are always energy minima. Continuous change in the energies or stresses, as illustrated here, are interrupted by discontinuous changes, and those are going to be the objects of our analysis. Okay, so the model system we look at is a well-studied glass former called the Cobb-Anderson binary Leonard-Jones mixture, and we study this over a wide range of system sizes, and as I already mentioned, we start with liquid configurations at 2 different temperatures, and we subject them to energy minimization to obtain the initial conditions for what we do. And the cyclic shear, as I said, is characterized by a maximum amplitude of strain, and we vary this number between roughly, well, 2% to 20%, and in small strain steps of 2 times 10 to the 4. And there's something wrong here. Okay, now, so we look at the configurations typically at the end of each cycle. So that's what gamma equal to 0 means. But as the number of cycles increases, what we call the accumulated strain, which is the strain, total strain through the cycle times the number of cycles, increases, and this is kept track of. It's called the accumulated strain. And like I said, we typically look at stroboscopic configurations, that is at the end of each cycle. Okay, so this is sort of a cartoon of what we're doing. This is the real system, and this is a 2-level system which is undergoing cyclic deformation. And okay, that's good enough. Right, so just as a preamble to what I'm going to say, I mentioned a couple of early works where firstly the observation that was made in looking at supercool or low temperature liquids is that deeper energy minima are sampled as one goes beyond or below characteristic temperature. So one can meaningfully talk about glasses as being more and more annealed when obtained from instantaneous liquid configurations equilibrated at different temperatures. And when you take these configurations, these now are shown here, different initial conditions, and are uniformly sheared, one sort of reaches some asymptotic high energy state, and this was characterized as rejuvenating the samples with shear deformation. And this is by no means the first work, it's just one of the early works which we sort of took as our starting point. A somewhat more complicated picture emerges when instead of just shearing in one direction, one shears back and forth, and this is from the work of Lax and Osborne, and basically what energy you end up with when you cycle forward and then back depends on a lot of factors, depends on the initial glass that you start with, how big the amplitude is, etc. So what we began by asking is, if we were to not just do this in one cycle as Lax and Osborne did, but do it over a number of cycles, what happens? Okay, so here is a quick summary of what happens. What I'll be showing a lot is data where there's a maximum amplitude, like I said, that varies between 2% up to 14% in this slide, but it could be a little bit larger. And in each case, we look at the properties of the system as a function of the number of cycles looking at stroboscopic configurations. And what you see is at very small amplitudes, the energies decrease. This is now starting with a poorly annealed glass, and then sort of saturate to some value. And likewise, when we start with a well annealed glass, the energies change a little bit, not very significant. The important thing to note is that when we go to larger amplitudes, these energies converge to a common value regardless of what initial configuration I start with, and so the system is somehow reaching, in quotes, an ergodic state, right? So the final state is independent of what I started with. And the amount of time that I take to reach this final state seems to show an apparent divergence across some threshold transition amplitude, and this is between 7 and 8%. And so there is something changing drastically at that strain amplitude. Okay. So we also look at how particles move as a function of the number of cycles, and treating the number of cycles as a time variable, we can define a mean squared displacement, and from that a diffusion coefficient. And these mean squared displacements, again, above a certain threshold amplitude of about 8% here, reach a common final state regardless of initial conditions, and more importantly, the mean squared displacement is linear in the number of cycles. Again, I emphasize we're looking at configurations one at the end of each cycle. And on the other hand, at smaller amplitudes, the mean squared displacement saturate and the system becomes localized. Okay, so if we plot the diffusion coefficient obtained in this way as a function of the amplitude of strain, one finds that in the higher strain amplitude regime, there is a finite diffusion coefficient that abruptly goes to 0 below a certain strain amplitude. I know you're smiling for a reason. So the fact whether this was a sudden jump or not was not very clear, but work of Kawasaki and Berthier showed that this was a sudden jump, and we've been subsequently able to confirm that to be the case. Okay, now talking about the yielding transition. So I mean, at this point I've sort of told you that there's some transition that's happening here in the system, and so the question is this the yielding transition? And in order to talk about this, we first go back and look at sort of the conventional way in which one talks about this, which is to look at stress strain plots. And here I show that the two initial samples that I have, the poorly annealed glass and the well annealed glass, at two different system sizes for cross check. And basically in both cases there isn't a very clear point at which one can identify a transition to have happened. This picture is in contrast with what one finds in looking at cyclic deformation. And here, in order to make a similar graph as this, we will look at the maximum stress that is achieved for any given strain amplitude, and those points look like this. And what you see is clearly a sudden drop in the maximum stress value across what turns out to be the same threshold amplitude of strain. These points could in principle be lower. We just don't get there because as I mentioned already, the time taken to reach these asymptotic states gets larger and larger as we are close to this transition. Okay, so here is a summary of a lot of different cases which illustrate the same point. So let me skip. So if one looks at what's happening through the cycles and through the strain range in each cycle, one has a picture like this, where one starts out with a high energy, and through the different cycles one is basically at an amplitude below the yielding transition, annealing the glass to lower and lower energy values. But when the amplitude becomes bigger than the threshold amplitude, one has a very different picture, where these energy curves sort of bifurcate into two lobes, where the energy at which the strain at which the lowest energy is reached becomes finite rather than zero. Okay, this indicates the emergence of plasticity, and so this is probably a little difficult. So if I start from a small amplitude and I keep increasing the amplitude, I go down from the black to red to blue, green to blue, and then I have this change in character, and the energies go up again. And likewise, the strain at which the minimum energy is reached is asymptotic to 0 for small amplitudes, but becomes finite and increases as I go to larger amplitudes. Okay, and this is the picture for the energies. There is the threshold strain amplitude at which the energies are minimum, and okay, so that's sort of a characterization of the transition we're looking at. Now I want to talk about avalanches. So basically this is again a familiar picture, and we look at these drops in stress or energy to identify plastic events. And when one such event happens, well, I'll tell you in a minute how we go about and look at look at the avalanches corresponding to them. So just to quickly say, I don't think I have time, this has been looked at a lot in the steady state regime under uniform shear, where one can sort of infer some relationship between the size dependence of the strain intervals or the stress increases between successive events and the energy drops. And this is something that we also find. I won't dwell on this. Okay, so how do we identify avalanches? So in addition to looking at energy drops, stress drops, we also try to identify the regions in space and their sizes where plastic deformation occurs. And we do this by looking at the distribution of displacements of particles when one of these energy drops occurs. And we find this to have a power law small value region followed by an exponential tail, and there's some argument for why this should be the case. I won't say it right now, but we look at the crossover from the power law to the exponential to define a threshold, and any displacement that's bigger than the threshold is a particle that has moved within a plastic core, okay, and the rest are elastically displaced particles, and we do by this process we identify clusters of particles that moved in an avalanche, and we look at the distributions of their sizes, and here they are. For a small system size, as we increase the amplitude of strain, the distributions look familiar, but nothing significant happens when we cross the threshold strain, okay. On the other hand, when we look at a sufficiently large system, we begin to find that the avalanche distributions sort of fall into two significantly distinguishable categories, and we can look at how the sizes of these the mean sizes of these different cases behaves as a function of the strain amplitude, and also as a function of system size. I'll come to that in a minute. But based on the expectation that avalanches scale as n to the 1/3 in the steady state regime, we scale our data to that expectation, and we find that indeed all the different system sizes in the above threshold regime fall on that predicted scaling, whereas at smaller amplitudes you see that in fact the avalanches are finite, and dividing by n to the 1/3 takes them to lower and lower values as you go to larger system sizes. We can also scale the avalanche sizes by their mean value and multiply by the expected power law, and one sees that there are indeed two completely distinguishable distributions of avalanches. What? Yeah. Okay. So let me skip these. So the energies do the same thing, but there's an interesting wrinkle. If I look at the energy drops as a function of strain amplitude for different system sizes, one sees in fact an independence both below the yielding amplitude and above. but if we follow then a procedure of identifying what the energy change in the plastic core of the plastic event is, and then we do see a behavior that's consistent with what I showed you earlier, where there is no significant system size dependence below, whereas there is above the yielding transition. And now here's something that I don't understand. If you look at the total energy drop and look at the size dependence, at high amplitudes you have this n to the 1/3 scaling. At smaller amplitudes, a priori it's not very clear what the n dependence should be or whether there should be any at all. But what you see, and this is something that I don't understand, is that the total energy drop below the yielding transition has a linear dependence on the system size. Okay. Okay. Now comparison with uniform shear. This is now not the best. We didn't study this very thoroughly, but basically to illustrate the point that for the poorly annealed glass and the well annealed glass, the energy change, sorry, the energy drops look very different. And both as a function of, okay, so if I look at the two different initial conditions, they look very different. In particular, for the poorly annealed glass, there isn't very much indication of where the yielding transition is, and the distributions also, in the case of a well annealed glass, look distinct between for small strain, for a window of strain which is small in value and a window of strain that is larger, whereas for the poorly annealed glass this is very difficult to tell apart. And okay, now so one question at this point is, there have been a lot of discussion about the avalanche sizes diverging as you come from below towards this yielding transition, and one may ask, so what happened? Certainly, if I look at the poorly annealed glass, there are very large avalanches even from the beginning, but where did they go? And the quick answer to that is, as you strain cyclically the glass, the energy drops decrease with the cycle, okay? And so do the stress drops, and we can also separate the energy jumps between the plastic and the total, and also look at the sizes of the events that correspond to them, and these are basically decreasing as the system gets annealed. And okay, so this I will not cover because I don't have time, and it wasn't actually the part that I had in mind to talk about. But let me quickly sort of talk about okay, actually the only thing I want to mention here is that you do have shear banding at the point of yielding, and this shear banding is robust also if we go beyond AQS and look at finite temperature, finite shear rate simulations. And now, as you heard a little bit in the morning, the shear banding, not in the same sense, but in the sense of stable shear bands as you increase the strain, has been discussed by various people as something as arising from a competition between annealing and rejuvenation effects. And okay, now so the shear bands that we see in cyclic deformation has not really been analyzed very much, but as you will hear tomorrow, even under uniform shear, for very well annealed glasses, you see shear bands. And there is a study that looks at an SGR model for cyclic deformation, where again they say that the shear banding there, which are stable, arise from a competition between aging and rejuvenation, but the sense in which this is incorporated in this model is not necessarily the same as what we have. So just to say a little bit about what annealing effects we do see. Here is the change in energy as a function of the number of cycles. This is just redrawing the data that I already showed, which shows that there is in fact a 1 over n scaling of the energy change from cycle to cycle, which will give you a logarithmic decrease in the energy. And so one can ask, is this only a property of cyclic deformation, or are annealing effects also important when one is looking at uniform shear deformation? And this is sort of not something that I would hang my hat on, but this is something to put before this audience to sort of think about and talk about. Even when one does uniform deformation, if one looks at the energies, certainly for the poorly annealed glass, so the energies go down, and this is not a good way of talking about it. So what one should look at is the zero strain value of the energy, and we make an effort to sort of estimate what those are, and those energies clearly do decrease. So in other words, even under uniform shear, there are annealing effects going on. Whether this is always the case and how much of a role it plays in whatever phenomenology one discusses is up for debate. So here's my summary. So the yielding transition appears to be a sharp transition associated with abrupt divergence of the sizes of avalanches, but abruptly at the yielding transition rather than approaching it. Avalanche sizes vary strongly during the approach to the steady state. The steady state behavior in cyclic shear is significantly different from uniform shear. Strong and significant annealing effects before and after the yielding transition, etc. So let me stop there. I don't want to. I want to leave a couple of minutes. I'll take any questions you have. Yeah. So here, you know, in the basic, the results that I presented, there are no thermal effects, like I said at the end. Something like shear banding does seem to happen also when you have finite temperature. But basically, okay, I mean, this is a hand-waving sort of explanation. However, so if you sort of have in mind a picture that better annealed glasses will have a larger yield strain, as you anneal the glass, there is sort of a limit up to which you can accommodate the strain that you're applying by annealing the glass to lower states. But there is a threshold, there is an a point of mechanical stability for any glass that you may have. So for a for a given gamma max, I'm either below yielding or I'm above yielding. That does not change, right? So I'm just saying now if I vary gamma max, I ask why do I, beyond a certain point, increase the energy? The reason is that the system is yielding, and then you can ask why does it yield? And then the answer that I gave will apply. That's correct. Yeah. Sure. Okay, so I don't know if it's a direct, so you're right, the first part is, you know, the number of events, the number of regions that plastically deform during a cycle go lower and lower, approaching zero, I suppose. And but the change to having when the system yields, I'm looking for a particular slide. The fraction of the system that takes part in this is substantial for this size simulations. So there's number of particles in the shear band jumps from 0 to 20% of the system. So I don't know if there's a gradual change of activity that prompts these regions to form. What you have is a sudden emergence of a shear band. Mm-hmm. Right. Yeah, this is a question in my mind. We haven't seen anything to sort of indicate that that's what will happen. But if, well, okay, so there could be some subtleties associated with the conditions in which you're doing. So what we are doing is constant volume, and there, in fact, what we do see is that there is a density change within the shear band. I didn't have time to talk about, but it's not 0 to from finite to 0. But I guess I don't know. I mean, this is a question. I was also, Ludovic was asking this question earlier. I don't know whether that will characterize a qualitatively different picture.